So welcome to the webinar, and thank you, Juraj, for allowing us or giving the opportunity to present our paper. So this is Soumya. I'm working as a postdoc in Pieve. So this is a paper that we have. So this is our co-author, and we have a team of PQC and QKD. So myself, Sebastian, Nick, Catherine, Bruno, Fiona, Boris, Chico, Simon, and Adelfonso. So we have surveyed 14 use cases across 8 countries, and so this is a table of contents where we will first briefly discuss about the motivation and contribution of this paper, and then Sebastian will discuss the security properties of the cryptographic scheme, some assumptions of QKD and PQC. Then we will go to the use case analysis framework. Somebody message, cannot see the screen. Everybody can see the screen.
I could ask Gabinet Paulette to unconnect and connect again because the sharing works fine for the rest.
Okay. Thank you. And then we will just discuss some of the use cases that we have used and give some comparative insights and some recommendations. So our motivation is when we see, when we Google it, that there are lots of use case paper, one from GSMA, one from standardization of ITU, HC has some paper, Madrid has some papers. So we see that for all of these use cases, this is only the description, no concrete security goal is there, and no comparison with post-quantum cryptography, and some of the use cases are only theoretical. So that is the basic motivation for us. That is why we surveyed and we try to answer these questions. Now I would like to hand over to Sebastian to continue this paper. Sebastian, you can.
All right, thank you very much, Soumya. I hope you can all see the presentation again. So yeah, I will be talking a little bit about the more cryptographic background to this paper. And of course, as I'm sure that all of you know, the biggest threat that we see right now from quantum computers comes from this harvest now, decrypt later attack. We have Alice on the left-hand side here, and we have Bob and some encrypted messages sent between them. But our adversary, Eve, is able to record that message, store it in her database, and then later, when she has a quantum computer, she could potentially decrypt the message and read all the contents of everything that's happened. So to protect against this, we have to switch over to new kinds of cryptography. Yeah, a little bit on, I'll talk a little bit on the background of this paper about how we look at cryptography typically, and then I'll also take a brief look at comparing the best known QKD solutions with the best known PQC solutions. So when we look at security, we can sort of classify how secure something is in more than one way, but one way that's interesting in the context of QKD is that we can look at what the computational power is that Eve has. And if Eve has no bounds on how much computation she's allowed to do, we say that she's computationally unbounded, and we talk about information theoretic security. On the other hand, if Eve is computationally bounded, we talk about computational security. We can further split both of these classifications further. So we can talk about perfect security when there's no success probability for Eve in whatever she's trying to do. So for example, to learn the contents of a message, if it is encrypted with a one-time pad, she learns 0 information. On the other hand, sometimes Eve has a small statistically negligible success probability, and then we talk about statistical security. So in this category, there are things like information theoretic secure max or one-time max. On the other hand, we can also split up computational security, where we talk about post-quantum security if Eve has access to a quantum computer. So these are the new schemes, the MLChem, MLDSA, stateless hash-based DSA, but also symmetric primitives such as AES and SHA-3 fall under this category. And on the other hand, we can also talk about classical security, where Eve is only assumed to have a classical computer. And these are the things that we want to replace. So this is RSA, Diffie-Hellman, or elliptic curve-based cryptography. Okay, I see some messages that there's issues with the sound, but I'll try to speak up as much as I can. All right. So let's talk about the cryptographic primitives that we have to our availability as cryptographers. And once I've talked about both symmetric and asymmetric cryptography, I'll see where QKD fits within this ecosystem. All right, so the most basic security property comes from encryption. We want to hide the contents of a message. So what can Alice and Bob do? Alice can take the key that she shares with Bob and then encrypt the message and then send it over to Bob. And Bob can use the same key to decrypt again. Now, as I already said, there's a one-time pad which can do this. And as I said, this is perfectly secure. However, there's a downside, and that's that the key must only be used once. And also that key has to be as long as the message itself. On the other hand, if we only need computational security, post-quantum security, then we can fall back to something like AES. And we can do this in CBC mode, counter mode. We can talk about CHA-20. There's various symmetric cryptography schemes out there. And they reuse the same key, and that key is very short. The next primitive that I wanted to mention is the message authentication code. Now, the message authentication code is something to preserve the authenticity of a message. And what happens here is that Alice is going to take, again, a key that she already shares with Bob. She's going to compute this code, the message authentication code, and out comes a little tag. That tag she appends to the message, and then the tagged message goes across the wire. And now Eve, our adversary, should not be able to modify this message or inject her own message without having Bob detect this. So Bob is going to recompute the MAC and check if it's the same as the one that he received. Now, we can do this with information theoretic security, and the so-called Wegman-Carter MACs actually achieve this. But again, there is an issue that keys there must only be used once. However, unlike the one-time pad, the keys are short. We can also talk about computational cryptography, computational MACs, and examples here would be HMAC or Poly 1305 with AES. Those are post-quantum secure, and again, they can reuse the same key, and that key is short. But of course, if we are actually encrypting data, we are typically interested in both the authenticity and the confidentiality of message. And this is why typically we want to use authenticated encryption. And essentially, this combines encryption with those MACs. So for example, we can again do this with information theoretic security. So if we combine the one-time pad with information theoretic secure MACs, we get statistical security, with again the downside that the key must only be used once. But if we use computational crypto, we can run, for example, something like AES in Galois counter mode or CHA-20 with Poly 1305, and this would give us post-quantum security and lets us reuse the same key. All right, and there's one more primitive, symmetric primitive that I think is interesting in the context of QKD, and that's the pseudo-random generator. Now, what this does is you take in a small key, so this is here indicated with the green key. You put that into the pseudo-random generator and you generate a longer key, or equivalently, you generate multiple keys. And these schemes can be made from things like AES, and therefore they are post-quantum secure. Now, especially in the context of QKD, it's interesting to look at if we get look at symmetric ratchets. So what does a ratchet do? Well, essentially we take the PRG again, but now we take part of that output and we're gonna replace the key that we already used, the green one, which we have to discard, and we're gonna replace that with a new one, the blue one. And then what we're left with, this red key, we can use that to encrypt data. So those are the symmetric primitives that are interesting. That brings us to the asymmetric ones. And asymmetric cryptography is characterized by the fact that there's no longer shared keys, but instead users have a key pair. So Alice in this scenario has a secret key indicated with the key symbol and the public key indicated here with the padlock symbol. And now she's going to give her public key to Bob, and she doesn't need any confidential channel to hand out her key. But she can essentially sign messages now. So this should look very familiar because it looks a lot like the Mac. She computes a signature on her message, and then she concatenates those, and she gets a signed message, which she can then send across to Bob. Now, these are achieved with post-quantum crypto primitives such as MLDSA and SLHDSA, and they provide us with post-quantum security. And now we get closer to QKD, but there's one more thing I wanted to talk about, and that is authenticated key exchange. So now we're no longer talking about just a single primitive, but we're actually talking about a full protocol. However, I've tried to sketch this as simple as possible. What happens in an AKE is that Alice takes her private key or her secret key, and she takes the public key of Bob, and she uses those as input into the AKE protocol. Now Bob inputs his secret key and Alice's public key, and out come what's called a session key. So this red shared key is now a private key that is shared by both Alice and Bob. And the adversary, for security, it's important that the adversary cannot distinguish this from a uniformly random key, even if the adversary interacts with our participants in many different ways. So even if Eve replaces some messages or tries various tricks, there's nothing she should be able to do. Now this gives us post-quantum security again. And two notable primitives here are TLS, for which we do have post-quantum versions, or PQXDH, which is what's happening in the handshake of, for example, of the Signal protocol, which is deployed in the Signal app, but also in WhatsApp. All right, and that brings me to QKD. So what does QKD do for us? So QKD here, I've drawn it here where we assume that Alice and Bob already have a pre-shared key. So what happens? We take QKD, which is an interactive protocol. Now first, Alice and Bob will somehow exchange some quantum information. And I've drawn it here as a send and prepare, send and measure protocol where Alice sends the qubits and Bob measures them. But there's various protocols which use entanglement and different kinds of quantum information exchange. But all quantum key distribution protocols subsequently will have post-processing. So in this post-processing, this is an interactive protocol where classical messages are exchanged to do things like information reconciliation and privacy amplification. Now, in order for Alice and Bob to know that they are indeed communicating with each other, it's very important that this post-processing is authenticated. So how can we do this? Well, we can essentially just MAC the entire transcript of the protocol. And this is a way that Alice and Bob can verify that they are communicating with the correct people. Now, they can do this with a key that was somehow distributed like a pre-shared key. So maybe they got this from a trusted courier, or it was installed on their devices when they got their QKD boxes. And then we can essentially use QKD as a ratchet, because now we're going to take that key, and this is a very long key, and we're going to take a little part of that, and we're going to put this back to authenticate the next QKD session that will occur. And then we are left with with the session key, and we can use this to encrypt data. Now, QKD used in this way gives us statistical security. However, sometimes we cannot assume that pre-shared keys are realistic, and in many scenarios we have to fall back to public key cryptography again. But again, here we can actually use QKD. So the idea is that we are going to do the same protocol, but instead of authenticating this post-processing with the MACs, we're going to authenticate it with digital signatures. So again, Alice and Bob now input their private key and each other's public key, and both of them are going to put a signature on the transcript as it's happened. Now, this means that this initial session no longer has statistical security. Instead, it gets post-quantum security. But what we can do in this scenario is that we can then take part of the QKD output, feed it back into QKD again to authenticate subsequent sessions. And now these subsequent sessions will have statistical security, but only if the initial session was not broken. So formally, really, we still get post-quantum security, but if the initial session wasn't broken for some reason, then we do end up with statistical security. All right, so in order to do full comparison, I think it's also important that we compare some of the assumptions that go into QKD and into PQC. So for QKD, we assume that quantum theory is correct and complete. And in the paper, we sometimes highlight this fact by talking about quantum information theoretic security. On the other hand, so this is something that we really think is quite secure. On the other hand, implementations may have issues. And this is something that we see in the field of quantum hacking. So sometimes it may occur that hardware leaks information about, for example, encoding bases, and that leakage is going through side channels. On the other hand, there's also the security proofs which are provided for QKD. They assume certain properties of the hardware. And if the hardware is not close enough to this ideal device, then the security proofs don't hold. So there might be, there could be enough leeway there for an attacker to exploit and break the protocol. A third assumption that we see quite often is that if we want to do end-to-end QKD, we are requiring that Alice and Bob have this long-distance quantum channel. And QKD is somewhat distance limited. So not always can we do QKD between the endpoints. Now, there's two solutions to this, as far as I'm aware. The first one is to use quantum repeaters. And these use techniques like entanglement swapping to set up long-distance quantum communication channels. However, these are not ready for practical use. I think there are some small-scale demos in laboratories, but not for large-scale deployment. So instead, what many people do is when they build larger quantum networks is that they use trusted nodes. Now, trusted nodes, as cryptographers, make us quite uneasy because there is a violation of the end-to-end principle there. Now, the fourth assumption, which is sometimes made in the QKD literature, is that that authors will state things like post-processing goes over an authenticated channel. But as I've demonstrated in the previous slides, depending on whether we have pre-shared keys to establish this authentication, or whether we have a public key to do digital signatures, we get some very differing protocols. So I think it's important that when people state how the authentication happens in QKD, what exactly do they mean for this? But PQC is also with some assumptions, and the biggest one is that the underlying mathematical problems on which we build this cryptography is hard, and we don't have absolute proofs for this. So these can be assumptions on the difficulty of learning with errors. There's assumptions on cryptographic hash functions for other types of cryptography. There's assumptions on decoding errors for error correcting code cryptography. But also our symmetric primitives that we use do have to be secure in a computational sense. And indeed, these assumptions, while they are not as mathematically crisp as some of the other assumptions, they are computational assumptions, and we have to assume that those are secure until a formal proof exists or until someone finds a way to break these assumptions. Now, I mentioned secure implementations for QKD, but this is also an issue for post-quantum cryptography. So in the cryptographers typically talk about side channels here, and we typically classify these in remote side channels where a remote adversary doesn't have direct access to the device that is doing the crypto. So these could be timing-based side channels. But there's also local side channels where we give the adversary partial access to the device, and they can do things like measure its power consumption. And we should still have security if the adversary gets this access to the cryptographic operations. On the other hand, PQC also has key authentication, and I haven't really mentioned this yet, but there is a big assumption in this asymmetric cryptography. When Alice hands out her public key to Bob, Bob needs to know that the public key that he has actually belongs to Alice. Now, there's various ways we can achieve this so-called key authentication. One is a public key infrastructure, where we have a trusted root of security, which would be the certificate root, for example, in the TLS protocol. We get a public key of this root installed on our devices, and then through that we verify that the key that we get is actually belonging to the person that we think we are communicating with. On the other hand, we can also have out-of-band key confirmation. So this is again something that happens, for example, with the Signal protocol. Here, Alice and Bob set up a secure channel, and then they can compare the security codes, or you do this little ceremony with the scanning the QR codes to verify that you are indeed using the correct public key. All right, so we can talk about the security guarantees that we get from various cryptography. Now, one thing that you may naively do is to just use a key and use it to encrypt all your data, but this gives you no forward secrecy. If that key is compromised, not only will all your future communication be compromised, but also everything that you've encrypted in the past can now be decrypted if it was recorded. So therefore, typically in these protocols, we want forward secrecy, or sometimes also called the key erasure property. So if we compute new session keys for a new communication, and then we throw away that key after we're done with it, if our device gets compromised, then we don't leak the session keys for earlier communication. And if that is computationally independent from the previous material, we get forward secrecy. Post-compromise security goes in the other direction. Some protocols allow us to recover when a key is compromised. So when a device gets compromised, we are going to be insecure, but for some protocols, if the adversary doesn't intercept the new key exchange that is happening, then we can be secure in the future again. And the last thing, I already alluded to it before, is everlasting secrecy. So this is something that we can get from, for example, QKD with digital signatures. If somehow we assume that this initial handshake was happened securely, and we have some reason to believe that it is, then all the encrypted data that is then encrypted using those keys will have information theoretic security. However, there is of course the big if, that we do have to assume that the initial handshake happened securely. All right, so that brings me finally to the things that we are trying to compare in this paper, at least from a theoretical perspective. The 6 protocols that we think are interesting in the context of QKD. So first protocol is actually very simple. In some scenarios, in some of the use cases we see, it's just viable for 2 parties. If you can establish a pre-shared key, you may as well establish enough to encrypt all the data that you're going to encrypt. And if you use information theoretic secure encryption, then essentially you can just encrypt all your data and be perfectly secure, statistically secure. For the next scenario was we still assume that pre-shared keys are viable. However, maybe it's not viable to share enough key material to encrypt all your data, but you can fall back to computational cryptography and use symmetric crypto only to set up this ratchet and encrypt data continuously. And the third scenario we have here, we establish QKD with this pre-shared key, and we're going to encrypt the data with information theoretic encryption. With the fourth scenario, we're going to bootstrap QKD using these signatures, but then we're going to continue with information theoretic QKD, and we encrypt the data with information theoretic security, information theoretic secure encryption. The fifth scenario is where we do the same thing with QKD. So we bootstrap from these signatures, but now we're going to encrypt with symmetric key symmetric cryptography, so AES in GCM mode, for example. Now, the reason we might do this is that the QKD key rate might be too low to keep up with the data rate that we're trying to encrypt, and therefore we fall back to this symmetric cryptography. And then the sixth scenario is where we just use PQC. So we only have post-quantum secure cryptography. And now we can compare these six scenarios in terms of what kind of security they provide us. So the first scenario with pre-shared keys gives us information theoretic security, it gives us everlasting secrecy, forward secrecy, but it doesn't provide post-compromise security. We can, of course, also initialize with a pre-shared key and then use symmetric cryptography. Then we only get forward secrecy in these four classifications. If we can use pre-shared keys and we can do QKD with information theoretic encryption, then we get all four properties here: information theoretic security, everlasting secrecy, forward secrecy, and post-compromise security. But if somehow we cannot we need to bootstrap from signatures with QKD, we lose this information theoretic property, but we're still left with everlasting secrecy, and again, forward secrecy and post-compromise security. But if then in the fifth scenario we use QKD, but then we also use computationally secure data encryption, we no longer have any of this information theoretic secure properties, not even everlasting secrecy. And this, in this sense, this is comparable with the post-quantum scenario that we see, where we just use a post-quantum authenticated key exchange and then use computational encryption on the data. All right, so I think that gives you enough of a background on the work we're doing, and now Soumya will again tell you more about the actual use cases that we analyzed.
Yes, so thank you, Sebastian. Can you see the screen?
Yes.
Yes, it works.
Yes, fine. So thank you, Sebastian, for briefly outlined what is the prerequisite to analyze these use cases and what are the different types of schemes that we can do for all of these use cases. So first, so I will share that what is the analysis method that we will follow here. So when we are analyzing some use cases, we ask several questions from the key usage point of view, from the first key usage point of view, from the networking point of view, and the security point of view, right? So for key usage point of view, the first question is that how or which type of data needs to be protected, right? Is it for long-term data or is it for short-term data, right? And what is the key that is used to protect this data, right? And the next, like how we are going to protect this data. What is the QKD protocols or the other AKI protocols that are used to protect this data? And what are the additional cryptographic protocol that is used in this method? And finally, using this method, how long we can get the protection so that it can mitigate the HDNL attack. For a networking perspective, we would like to ask the question like, what is the basic network topology for this use case, and what are the QKD protocols they are going to use, whether it's a CV1, DV1, or the other ones. And finally, as Sebastian was discussing, what are the security guarantee that the system can provide, whether they are providing confidentiality or authenticity. So what is the security goal? So next, we have surveyed all the use cases that are available from the internet, from different manuscripts, from different companies' website as a use case. And finally, we have listed that these are some use cases that that can answer that has some information where we can answer the queries that we make for each of the use cases. Some of the use cases are good, some of the use cases are very limited. For example, the first use case is the authenticity of election research started in 2017. Then there are some use case of backup. Finally, there are some genome data use case, some use case on self-driving car and grid network. So I will only discuss this blue use case one because these are interesting, and for rest of the use case analysis, we refer to the paper. So the first use case is the authenticity of election result. So this is in Switzerland. So the motto or goal of this use case to send the information like how many votes has been is been done from the central ballot station to the data center, and they have used HMAC for authenticity and QKD plus AES-256 for confidentiality. So, and the distance they have covered is 4 kilometers. So now, so what we find that they are actually, so what is the type of data they are using? They are only sending the number of votes from one place to other place. And once the election is done, then this number of votes is made public. So then it is the public data. So we don't need to actually protect this data for longer time or for say longer period. So harvest now decrypt letter or HTML attack does not apply in this use case, right? So again, we see that the goal of this use case that to protect the data during transit, right, is the what is the number of ports. So for this, QKD already use authenticated data channels. So that will be enough to meet the security goal, right? So that's what we say that this current use case has very limited value for the QKD. So what can be a better future scenario that if we can transmit the votes during the voting for a say, digital voting system from one place to other place, then we need a confidentiality and possibly use QKD. But that will introduce like other security concern or attack vector, like when a person is voting, by analyzing that vote, they can leak some privacy information. So if somebody considers a better version of this use case, they need to consider this additional attack vectors. Right. So the next use case, what we see in most of the companies or deployed things they are using, like they are using QKD for information storage during data transmission and storing into some separate place. For example, the facial biometric data they are trying to store on some place, and there are medical image sharing data, medical data backup, or the key storage backup. These are the use cases that is we classify this as a information sharing and backup use case. So for all of these use case, we have some recommendation. Like QKD is mostly used for transmitting the backup data, right? So this has a merit while transmitting from one place to other place. Once it is being transmitted, then for storing, QKD may be have a limited use, because then in the store you have to save the data with the key, and that may reduce the long-term security. So we recommend to a better version that encrypt the data before transmission with a static or pre-shared key. Then we don't need to share the key in the same place where the data has been shared, right? And if somebody uses asymmetric encryption for this data sharing, then the data sender does not need to keep the secret key to one place, and that is well known, right? And the final thing that we recommend, and some of the use cases they have already done this, that apply a secret sharing method, either it's a quantum secret sharing or a classical secret sharing, to back up the decryption key to different places, and that has been used to some of the use cases, so that multiple parties can come together, or the trusted board member can come together and recover the backup data. So these are the some we can say use case that QKD can actually apply. And then we will move to the another use case where the grid network to power station has been connected using this ID contact devices, and the goal is to have a secure data transmission and detect like attackers. For example, there is, if there is some attack, the goal is to detect whether we can detect the attacker using QKD. But actually, what we see is that this is the not a goal for QKD to detect the hacking or detect that whether some attack is done in the whole system, right? So for this use case, we cannot find a clear threat model or which are the type of data they are going to protect, right? And what are the attacks they have in mind? They wanted QKD to protect those type of attacks, right? So, and if what we suggest then that if you have a defined goal that what are the data you wanted to protect, that data needs a long-term confidentiality, then only use QKD for this for to protect this data in any of the schemes that Sebastian has already discussed. And since QKD is a very expensive technology, so once we are confirmed that okay, this can be deployed, this has a clear objective, this has a clear advantage, then we recommend to deploy QKD for this. And the next, there is a very good use case that securing the genome data. So genome data from the medical perspective is a very important data that we see, and that data needs to be protected for long term. So this type of data where you can actually say, okay, this HTML attack comes into play, and this use case has actually done this thing, this protection against HTML attack, where they have used OTP to encrypt the genome sequences. What Sebastian was asking, the third point for this, like QKD for the key transfer and OTP to send this data. So this is what we say a good use case where QKD has a definite advantage. And so yes, so what is our recommendation? Like we should the customers or the users should continue to maintain the QKD infrastructure and periodically see if there is fault is there, and that's all. So this is an example of a good QKD use case. And there is another example that was recently QRate company. They have published. So they have what they have done. They use QKD in a car to share a real-time telemetry data with the nearest, say, the station, power station, not power station, with a station where all this data for a self-driving car are stored, and they connect these QKD devices with this stations, right? So here the main security goal is to prevent the unauthorized access or tampering of this softwares that is being used for self-driving cars, and the motivation is here is good. If somebody can take or attack or hack this softwares for self-driving cars, then they can do some accident or do some bad thing using this. So there is a good motivation, but clearly this is not a scope for HDNL attack, right? So what is our recommendation? The first, since QKD boxes are too big now, and it is very costly to use QKD inside in a car, maybe this is for future when we have some cheaper version of this QKD boxes. And while the software update with the nearest station, that can be done, like that's the authentication problem. So we have to authenticate whether the software update is using the correct power station or correct station or not. So that can be done using an authenticated channel, right? So there is no need to use QKD for this, right? So these are the use cases that we have briefly discussed, and how we are using, like now you have a clear overview, like how to approach a use case, what are the questions you need to have in mind, and what are the security goals you have in mind. And here, so we have analyzed other use cases where we see that these data or the questions that we ask, these are not provided or is not there in these use cases. And some of the use cases is actually not a use case. For example, QKD as a cloud service. So you are giving your QKD key to some users, but this is not a use case. You are providing QKD for the keys for the users. So that thing we see that, okay, this is not a correct use case, or this has a limited usage as a use case, right? And there is another goal was security independence for the network, where we see that, okay, they share key into different paths, and if one path is broken or being attacked, still using other path, they can share the key. But this is a feature of the network. This is not a use case. And they have also not discussed how these two keys can be combined. What if one of the keys are broken? So these are the things that still needed to properly analyze, and we hope that this data will be available when these use cases they have upgrade these use cases, right? So in short, what we can say that QKD, okay, it's theoretical security without computational assumptions, but it has high cost, obviously, and we have to be very careful how we are using QKD. And since PQC is standardized, so it is very good to use PQC. But there is again a good threat like HDNL attack. If some of the PQC algorithm is compromised in future, then it will be again prone to HDNL attack. So what we recommend that organization or the users made very careful while you are using QKD or PQC, and choose smartly. That is our goal. And this we conclude the presentation and the acknowledgement. So we have acknowledged the Dutch Ministry of Economic Affairs for Climate Policy, EKI, and Quantum Delta NL, and by NWO, NWA project, and the FIX project. And also we thank to the anonymous reviewer who made their valuable comments while an earlier draft of the paper. So thank you all. And yes, now this presentation is open for discussions. So now we can, if you have some questions, I think we will answer one by one.
Okay, thank you very much for the presentation. It was very instructive, and I think that there has been a few notes during the meeting in the chat, but now is the open opportunity for you to raise your hand and pose a question directly towards our presenters. In the meantime, I will use the liberty to ask my first question. How do you think will evolve this distinction between PQC and QKD, and what technology advancements are needed to change the status quo of what you have now presented?
Sorry, I did not understand the question. So,
well, you made the comparison of where is better to use PQC and what are use cases which are good for quantum key distribution.
yeah.
What advancements do we need to change this comparison? I don't know, new quantum memories, quantum repeaters, or something like that.
Yes. So, yeah. So since QKD has so the first thing is as Sebastian has already discussed, QKD clearly has some disadvantage in terms of memory, in terms of what we can say the quantum repeaters, and if they are in place, so we will have some better use cases. But the what the intention of our this study is to before going into some use case, think critically that is this use case is good for QKD or good for PQC, and that was our motivation to make the audience or the community aware that how to properly choose a use case. So that was our primary goal of this presentation. Have I answered your question, or Sebastian, Nick, you want to add with this answer maybe?
Yeah, maybe I can add something there. I think really the violation of the end-to-end principle is one of the biggest problems with current deployments of QKD. And I therefore think that if we can get quantum repeaters, this will open up maybe more use cases. But we have to always keep in mind that we still compare them against the best-in-class solutions for post-quantum crypto. But then we can reassess some of these use cases maybe. Although I have to clarify that some of these use cases were already small scale, and therefore already they were end-to-end. So.
Thank you. Maybe I can ask Marko Johanni Saarinen to add on what he put into his notes. That he just made a remark. Why would we need to change the current technology? Or
yeah. So the point being is that QKD is of course older than PQC, and it's been always a technology looking for an application. It's a solution looking for a problem. So I mean, there's no you need to have a really strong leap of faith to ignore everything about theoretical computer science in order not to believe in computational hardness assumptions. So I mean, there's no like, it's not providing a solution even with these advancements to anything that I can think of that we can solve without it. So I mean, why keep funding something like that just isn't working out? So that was basically the point I was making.
Okay,
So if it doesn't work, if it's not useful, if we can't use it in mobile internet, everyone's using cell phones, etc. It's not solving problems that we actually have.
Thank you. Now I would like to ask Frederick Kerling. I can unmute the microphone. There is
Yes.
a question. Yes, it's up to you.
Yeah, I think I see already somebody answered or at least continued on my question.
Yes.
My main question was that indeed is this post-compromise security setup in QKD also mentioned in your paper as being a unique property of QKD. Is it just to resecure an existing communication tunnel, or does it do something deeper than that? I would like to understand it better.
Yeah, I can try to answer that. So first of all, this is not a unique property to QKD, and in fact, many post-quantum solutions do also achieve this post-compromise security. And indeed, as Stefan answered in the chat, the definition for compromise is really important here. So there's two definitions. If you look at the PCS paper from a few years ago, I'm sorry, I'm blanking on the authors here, but they define weak compromise where indeed we can use the long-term keys, but we cannot learn the long-term keys. So this would be in a hardware-based storage solution, for example. But there's also the other compromise where we try to recover from a full compromise, but then we somehow assume that the adversary does not maintain an active man in the middle on this channel. So recovering from full compromise is never possible, neither with QKD nor with PQC. But indeed, it is just a re-establishment of a tunnel that was already secure.
Thank you. So now we have a question from Stefan Röhrig from Schwarz Cybersecurity. Maybe you can rephrase it on yourself, Stefan.
Oh, it was mere a comment to the question from Fredericks, and I think it's already answered. And your comment, Sebastian, stated the same. So I'm fine. Thank you.
Thank you.
Okay, thank you. I also see in the chat that there was a question or a remark by Olivier Lemoud. I'm probably mispronouncing that, so I'm sorry. But he's saying that long distance quantum channels can also be established with satellites. So I want to comment on that, and that is that most satellite-based QKD systems that I've seen out there actually do simple prepare and measure between the ground station and the satellite. And then this key that is established in that way is then relayed to another ground station. So in that sense, the satellite acts as a trusted node. Of course, if we can use these satellites as a quantum repeater, then the game changes. So it is still a trusted node. However, because the trusted node is now a satellite, we need fewer trusted nodes to set up the end-to-end communication. But there is still a trusted node in there.
Okay. If you have some direct questions, just raise your hand or write it down. I can open your microphone one by one. I'm not able to open all the microphones at the same time. Okay, Marco is also reminding us about the question on firmware updates, because typically it's just a signed file which is sent and authenticated by the key. So why would we need this other approach?
Sorry, can you repeat the question?
When you have been presenting the part on firmware updates, the use case, you can elaborate a little bit more on this.
Yeah, so I think this is exactly the question we should be asking ourselves when we are going to replace existing systems that are not broken in practice. We better have a very good reason for doing so. And I think in order to be able to make a comparison just on the security level, we need to understand the exact security that's being added by these various systems. Currently, we just don't see enough of a good comparison being made there. But maybe once we do have such a clear security statement and can pinpoint the exact added value of QKD, then we can reassess if that is worth the cost that we need to pay to distribute this.
Yeah.
I hope that answers your question / remark.
If you see in the comment, there is a conversation from Marco.
Let's see.
I should be able to. Now I open the mic for Marco.
Yeah. So in the self-driving cars use case, it was presented this sort of a firmware update scenario, and of course, authenticity is the most important property of firmware, and most microchips nowadays have a ability to verify signatures, and I've been working with hardware partners, and since a couple of years ago, these signature verification processes have already been updated into post-quantum stuff. So that's kind of already a solved problem. So I using a QKD to transmit firmware updates seemed such a weird solution. So that was just a comment. And also in your slides, it was kind of not implied that public key cryptography would be used to secure firmware updates, which is actually what is being done. All of your apps and all of your programs that you download to Microsoft Windows, for example, they have signatures, and those signatures validate the authenticity of those programs. So this is just very basic information security.
Okay. I would follow up with Arash Brander. He's commenting on this remark by Marco. Question to Sebastian: was there a reason to do a cost-benefit analysis coupled with the risk assessment, which would be able to systematically answer the following question? It is at all to begin with justifiable to use QKD?
Yes, thank you. I think that's a very valid question to ask at this point. I find it hard to give a clear yes or no answer here. I think the cost is high, and I think we have to look at both practical and theoretical security. And I think we can only start to make a comparison if we really crystallize what the added benefit is of these systems. And to be able to do that, we really need to take the full cryptographic context into account. And we tried to do this within this paper, and I hope we succeeded in most of these. But there's just a lot of information that's missing still for us to be able to do a very clear comparison. So I think that is needed first before we fully dismiss QKD or fully implement it everywhere, essentially.
Yeah, I would like to ask Arash to follow up because he has more to add.
Thanks, Sebastian, for the answer. I mean, fair enough. I don't want to pick on what you said, but I think what comes across is that, first of all, thanks for the presentation and the good work. I think the question, let's say the comment by Marco, which is very relevant, is that this comes up quite often. And the second part of my question is more of a comment or maybe a suggestion, because it's also, I'm thinking about it as I speak now. I think a systematic way of addressing this question, which was already very useful in cryptography, there was this paper about 30 years ago by Russell and Plazio, where he looks at, essentially breaks down the world that we live in 5 theoretical ones, looking at the possible ramifications of different computational assumptions not holding. And it's a very nice way of, let's say, separating these theoretical worlds from other, and also it's a bit like the hierarchical in complexity theory of polynomial hierarchy, and it's let's say analogy in terms of analogy. And if you were to situate yourself such a solution, use cases, QKD in general, in such a context, we may be able to once and for all say something really in a manner that is robust enough, because whenever we jump into a use case and we look at, you've got a breakdown of the key exchanges, the way you can use them, data encryption. I could ask questions about why not combine it with such and such. It's a choice. It's a choice you make, and as long as it's consistent, it's fine. But that very fundamental question still stands: why should I? And the moment you answer one of them, you're maybe implicitly violating or assuming some assumptions that no longer hold. And I think in most cases, you would find yourself in a world where you will have much bigger problems to deal with than, let's say, such a key exchange solution would solve for you. And if you go back to that paper, even in that most pessimistic scenario, there are situations where we know, look, then if we live in such a world, well, so many of such problems can be solved using polynomial time algorithms, then this is all that we can do anyway. And then to ask, in such a world, would this still have any relevance? So as I said, the second part is really just a thought. And I think the first part in terms of the risk analysis is just that, and I think it's among the few works where people have actually bothered to do this kind of analysis. So it was something that was been badly needed for a long time. It still is use case oriented. And I think if we do this way of just zooming out and looking at, in an abstract way, what is it that you're trying to solve? Why do we think it's a problem to begin with, as Marco was saying? Is it really? And if you think yes, do try to think about what this brings about in terms of additional cost that we tend to just forget about. I mean, we just say, I want information theoretic security, even if we take it with a huge grain of salt about the security assumptions, which I'm happy to do because it allows us to do some comparison. You would still not be able to say much because you're not looking at the cascade effects of, okay, I replace this assumption with the other one. What happens to everything else that I'm relying on? Anyways, since I was unmuted, I just took the liberty to clarify a bit more, but I don't mean to take more time. Thank you.
Yeah, thank you for that comment. Yeah, no, great remark. Great. I think I follow your view there. And if we look, for example, at the 5 worlds, what my understanding is about that is that we replace computational assumptions with weaker assumptions. So we're still talking not about this information theoretic security, is my understanding, but more to the point of our paper, we just don't see those being deployed right now. We see QKD being deployed, and I think we have to look at the systems that are out there now and people are selling as security solutions. While indeed, if we use quantum information in different ways than just doing QKD to establish security, I think that's a very interesting and cool topic of research to continue to work on. But we have to keep in mind that here we are looking at security solutions being deployed in the field right now with QKD as it is implemented right now. So, but yeah, no, yes, great remark. Thank you for that.
Thank you.
I
Thank
can
you.
add one point here. So regarding the cost, yes, the cost is something we should look, but so QKD is an emerging technology. So as we can see, like a few years earlier, there is a comment that personal computers was so huge, so big, and there was some comment that people never own like a desktop, a personal computer in their home. But today we have a mobile phone at our hand. So I think this QKD technology has just started. So all this company has just did their solutions, and I think in next 5 to 10 years, when we have some mature technology, then the cost will reduce drastically, and the issue with the cost will be then comparable. So that's my personal view that I wanted to share. And obviously, currently, cost is obviously a factor.
Yes, thank you. Now I will move the microphone to Pierre Miller from CEST, which I think is interesting to learn what's the answer from Sumia on this question. Maybe Pierre, if you can say it on yourself.
Yes. Hello, everybody. Thank you very much first for this comprehensive presentation. Really appreciated. I just had a question towards basically the notion of quality of implementation, because indeed we are talking about two different implementation of technology, one being software-based purely, or almost purely, because we know that there's hardware acceleration usually at stake, and the second one being QKD, where we have not only confidentiality of the secret utility exchange, but also we can have a measurable source of entropy, where we can also prove the certain levels of randomness of the secret, which is ultimately provided to the customer. Therefore, I understand that notion of quality might be also an angle of comparison between both, because it's not taken for granted that a PQC algorithm of one software editor will be exactly the same quality of implementation as another, while basically for QKD, because we are talking about multi-million infrastructure, there will be certainly some certification at stake. What is your opinion about the need for certification on both technology, and can this be an angle of comparison of both technology?
Okay, I can start. Yes. So one of the major issue with what industry is facing using either say somebody other than, so forget about other issues. Somebody wanted to use QKD for their organization. There is a major issue of certification that is obviously missing, and PQC is now certified. So the companies is now can use PQC for their current system, and that the standardization is obviously a problem, and there are different standardization efforts are currently going on, I think, with HC, ITU, and I am also part of some of the standardization body from TUE. We have some people, they are working on standardization, and the obviously once QKD is standardized, then the organizations or industry, they wanted to use QKD as a solution, they can use it more efficiently. So that is my answer. Sebastian, Nick, you wanted to add something?
Yes, yes, indeed. I think that the establishment of randomness in both QKD and classical cryptography is just something that we have to deal with in both scenarios. Now, QKD and its generation of randomness are sort of orthogonal. So we can indeed do this with QRNGs, but then again, we can also do QRNGs to generate classical crypto. But just because it's generated with quantum randomness doesn't mean that it's always good. And there have indeed been instances in the past where QRNGs actually turned out to output biased bits. So I think this issue, while it's very interesting and should be worked on, is basically orthogonal to the question of whether or not we should use QKD.
Okay, thank you for your comments on that.
I see that some more discussion is open between the attendants in the chat. Anyways, if there is some last question you can ask, and otherwise I would wrap up, because we have run out of time mostly. But here is one more from. Okay, give me a second. I'm opening the microphone for. Yes. Now, Mr. Papadopoulos, you can ask yourself.
Can you hear me?
Yes.
Yes, so if we want to generate larger keys, I think that a lot of improvements are being worked on within the field of QKD, and indeed key rates are growing still. I don't know how to do this. Like, I'm not an expert on these kinds of things with QKD, so I cannot truly answer this, but I do know that key rates are always improving.
Yeah, I wanted to clarify the 3.3 case and the use case you presented with genomic data, where you mentioned that genomic data, for the genomic data, they used OTP with the QKD keys. I'm not sure how they do that, because it's not possible to have a XOR of a big data set, even a photo, with just QKD keys. Probably, I assume that they use the QKD key as a seed in the KDF system in order to generate a pseudo-random key, a bigger key. But in that case, if this is the case, then in 3.3, it's not information theoretical security. You can't argue that. So the use case that this 3.3 can support is very limited. Just send very small, very, very short messages. Otherwise, it's not information theoretic security, because it's not OTP, it's pseudo OTP, something like that. Thanks.
I think I can answer that question. So they actually did use XOR, but the reason they could use it was that the analysis of the genome data took very long. So it already took hours to analyze, and while this analysis was being done, data was generated, which took hours. So it took they had a very long time to send over this data. So there was also a lot of time for QKD to generate the keys. So they sent a lot of data, but this took like a day to send the complete data, because the slowest step was actually analyzing the genome data. So that's why it worked in this use case.
Okay, interesting. I will have a look at the paper then. Okay, thanks.
Maybe Fabiana de Pieve wanted to add something to the discussion.
Hi. Yes, so thank you very much to you too for this very nice seminar. I would like to ask maybe a very open question, but if possible, if there is anyone who would like to answer from both communities, I would be very, very happy to listen to any input. And if so, let's say that for the moment, many QKD links are indeed a sort of patchwork, an ad hoc design, let's say, with QKD using PQC for authentication. There have been also some recent papers, indeed, for the trusted nodes. This is reasonable for the status of the technology, although indeed, as you highlight, then the overall security of the procedure is not the one that one would like to have. But can we envisage, also referring to, let's say, the impagliazzo of 5 words, that we will be in a mixture of different words, and that we may want to, for example, do the opposite, use the QKD keys for public encryption, or in certain cases, indeed, continue with PQC supporting for authentication the QKD protocols. Can we envisage that, or even more, can we envisage that none of the two will actually continue to guarantee the security that we hope. Maybe because there will be some breakthroughs in cryptanalysis for PQC, or maybe because we will never be able to implement at a perfect level QKD. Can we envisage also the possibility that some other completely new foundations will be needed? And if yes, would these two communities be available to work together? Silence.
It's a very, very difficult question, of course, to answer. Let me, and please, some of the cryptographers in the audience, correct me if I'm wrong here, but my understanding is that we cannot build public key crypto that is information theoretic secure. You will always have a public key that is computationally bound to the secret key somehow. There are different ways of doing it. There are minimal assumptions that we can indeed do instead of the current computational assumptions we do, such as the existence of one-way functions. And yes, these are, I think, extremely interesting to continue to research. Yeah.
Okay,
Sonia, maybe you
that was a very balanced answer, but here I'm not looking for balanced answer. I'm looking for someone who launches himself or herself into the void and envisage a future where we may need completely different concepts and foundations. Maybe because indeed there will be some breakthroughs, not only attacking lattice-based PQC, but also schemes beyond lattice-based. We don't know, and maybe QKD indeed will, even with much improvement in the implementation, there will be also some other discoveries for new attacks, and I don't know. So, yeah, I'm trying to test the, let's say, the will of this community to, these two communities to work together for future networks that may rely on concepts that are completely different from those that we have today.
Yes, so I can try to answer this question. So from like a historical point of view, so initially we only had a private public key crypto system, and then Schwar's algorithm comes, and then it shows that okay, we cannot in some future, maybe when quantum computer will arise, this public key crypto system will broke. So we need to move to some information theoretic crypto system, and people started working say from 1994, and in 30 years they come up with a, we can say not a solution but a POC or proof of concept of a new solution, right? So now the question is, if we know, okay, then this QKD or PQC, this thing are in danger, we should again look for a new way to connect. And to answer your question, yes. So initially there was like only say PQC or classical crypto guys. Then some of them moved to the quantum crypto. And if we need some way to encrypt or say secure the communication, some of this person from QKD or PQC will move and work, and they will build the new encryption system, because that has been done in previously. So hopefully that will be done in future. So that is my understanding and my personal view.
Thank you. Someone who wants to speak? Arash. Arash is a writer and a speaker. Always. Arash, Marco, I see in the chat.
We see now quite fruitful discussion.
Yeah, Arash, maybe you want to say something?
Not really. I mean, somebody said that this should be the last comment or question, and I was happy to answer some questions in the chat. So, I mean, there are some valid points. I think we've established that a different kind of analysis would still be needed to add to the good work that has been done. So I don't have much else to add, really.
Okay.
And one more remark from Marco Johanni.
So of course we are in a situation where something like 40% of internet traffic is encrypted with PQC. So there was an adoption during last year. For example, my Android phone was silently upgraded last December, and all of a sudden it supported MLChem Geeksync, so we could have that, and all of the Google servers updated. And from this sort of a encryption in mass perspective, of course, that's all wireless communication. So there would need to be a serious physics done in order to somehow secure radio communication in order for us to be for QKD to be useful there. And from military viewpoint, they tend to be dismissive mainly because of this availability issue. So of course, in a sort of a war situation, the adversary will attack your communication links, and fixed links are very, very bad. So they have to kind of build things from the perspective that you can't trust the physical infrastructure to exist. So these are the main sort of key points that are preventing it from being used in like defense and also in mass. That we just use mobile phones nowadays. But on the other hand, there's also situations where you have a very contested situation with radio waves, like what happens in war fronts nowadays. So they're actually using fiber optic cables there, and then people have been looking into new kinds of modulation that might be able to bypass this sort of jamming techniques and other things that are available. So perhaps those new modulation techniques might be sort of QKD-like in some sense. I don't know, but that's just my take. But yeah, PQC is already used by billions. You and me, this connection is probably already with that.
Yes.
I see Christophe Marcard also wrote something. I don't know if he wants to.
And maybe I will first give the opportunity to Pierre Muller, and then let's see. Pierre?
Yes, it was just a comment, not really a specific answer, but I fully subscribe to your point of view. I mean, a collaborative approach is certainly the best way to get something that works at the end of the day.
Okay, thank you. And Christophe Marcard?
Oh yeah, just to mention a comment of mine. Of course, the big question is about the long-term security of PQC, right? I mean, and of course, one has to look at the use cases. Now, I think looking at some old use cases is a bit dangerous because I know that many in the community did not choose the use cases in such a way that you really want to highlight the advantage of QKD, but just more the applicability into various iterations in realistic environment, right? So one has to be a bit careful there. And what we do in the community for a long time and have been very successfully also talking to the German BSI, for example, is that we of course think about the benefit of QKD, about certification, about how to combine it with PQC, to identify how to use it, where to use it best. Definitely end-to-end encryption is one big point. For example, in metropolitan areas, it's not a problem at all to reach end-to-end encryption through optical switching and routing. So there's a lot of development that takes into account both communities, and I think that is very good like that, because definitely prices will come down, will be much more affordable. But again, of course, one has to be aware of the fact when to use which type of encryption, and that is valid, of course, for all these kind of technologies, right?
Interesting. Oh, wow.
So thank you, Christoph, for your comments. Yes, indeed, it's what you say is really good. So from our point of view, we focused on what are the use case that is being deployed and is active. So that's the way what we choose all the use cases. First, we choose all of the use cases which is been deployed, and then we filter out the use cases where we have enough information or not. So, and we from a QKD guy and PQC group, we both collaborate to analyze these use cases, and that is the result what we think was missing in both of the community, PQC community and QKD community. And the last point, I also agree that what we have done, these two community work together, and in future we should also work together and build end-to-end encrypted future. Yeah, thank you.
Thank you. Well, I would like to very much thank, first of all, to our speakers, to Sumiadas and Sebastian Verschoor. And I also would like to say thanks to everybody who participated in the discussion, which was very open and interesting. And I hope you will be willing to connect to our future seminars, webinars that we will organize in the future. Thank you all for participating, for listening, and the recording of this will be made available in a day. And then I will send a reminder with the link to everybody who has been connected today. Thank you, everybody. Have a nice evening or afternoon. Goodbye.
Thank you. Thank you.
Thank you.
Bye.
Thank
Thank
you.
you.
Bye bye.